I'll be right back with you all. I'm gonna start class here in just one or 2 minutes. Y'all hang tight. All right, good afternoon.
Good morning.
This is our last hurrah, huh, before the test,
Yeah.
which is, what's that, Thursday?
Yes.
Right.
Oh,
Already
did
stated
you
that.
get my message?
I haven't checked my email today.
Oh, okay. About I remember last class you were like, maybe we can have a whole like review together, blah blah blah.
I sent out an email with some
Uh-huh.
additional times that I'm going to be available
Okay.
for the whole class. So I'll look at your email later.
Yeah. Everybody was okay with Tuesday. Just let you know.
Okay. All right. So our test is on Thursday, 12:30. As far as the things that you can have on the test, your formulas from Canvas website off the files page. And then I'm also going to let you do a cheat sheet. Standard sheet of paper, front and back. You can put any sort of notes, steps, formulas, procedures on this piece of paper. You may not put worked out problems on the paper. Okay, it can't just be you working out a bunch of problems and that's your cheat sheet. It's just there as a guide to help you, remind yourself of certain things. Maybe like the mean value theorem, if you need to write that formula down, things like that. So as you work through the review, take note of things that you think you'll need and put that on that sheet. This sheet you will have to show to the camera and you will have to turn it in with your work. All right. Any questions on that?
No.
Okay. All right.
Thank
Well, let's finish up the semester. All right. So we were talking last time about antiderivatives, right? And how important antiderivatives are in Cal 2. And we were practicing trying to implement this thing called the power rule. And then there were some other antiderivatives that you should just know because of what you know from Cal 1 about derivatives, right? Like the antiderivative of cosine of x is sine of x, because you know that the derivative of sine is cosine. And there are certain ones that you should all be familiar with. So I'm going to throw a couple of more out here just to make sure we're all clear on these. So some common antiderivatives. All right, so what are some of the common ones? How about this one? We've already done this one. Here we're going to do little f, and then over here we'll do capital F, all right? So we already did this. 1 over x was a very special one, right? The antiderivative of that was natural log of x plus c. The next one, we didn't talk about this, but e to the x. What would the antiderivative of e to the x be?
E to the x.
Itself, right?
Mm-hmm.
Okay, plus c. Some other ones that should be pretty straightforward. Cosine of x. We all know the antiderivative of that, sine x plus constant. We had to be a little bit careful with sine x, the antiderivative of sine x. That
Negative
one
cosine.
Negative cosine.
is negative cosine. So the most common mistake Cal 1 students make moving into Cal 2 is that when they take the antiderivative of sine, they say cosine. But it's negative cosine because of the fact that when you take derivative cosine, you get negative sine. You have to account for that with a negative here. All right, so how about this one though? We didn't talk about this last time. The antiderivative of tangent x.
Cosecant squared.
Are you thinking of the derivative of it or the antiderivative of it?
Antiderivative. I was thinking that'd be the opposite of
Okay,
secant
so
squared.
maybe it's the opposite. Well, it actually turns out to not be something that we can do right now. All right, because there was nothing in Cal 1 that we learned that when you take the derivative of it, you get just tangent. We know the derivative of tangent is secant squared, right? But we don't know what the antiderivative of tangent is. So this over here, stay tuned, all right? You'll learn that in Cal 2, all right? Not here.
Filled with excitement.
Yes, yes. So what are, okay, then that means we're probably going to have a hard time with a lot of these. Like if we try, what are the other three trig functions? Secant x, the antiderivative of that. Again, there was nothing that we knew in Cal 1 that when you took the derivative, you got just secant. So this one, same thing. Stay tuned. Cosecant. Guess what? We don't know. Stay tuned. All right. What's the last of the 6 trig functions? Cotangent? Don't know. Okay. You're just going to have to wait a little bit. Now, there are some things that when we do see them, we should know what they go back to. Like this is what I'm trying to get at. There are some things that we knew from Cal 1 over here. Like if we had, let's see, tangent here, what would this have been over here? Secant squared x, right? So if someone wants us to give them the antiderivative of secant squared x, we can say that's tangent x plus c because we know the derivative of tangent was secant squared. And there's a couple of others that we would have known from Cal 1, like we do know the derivative of secant x. What's the derivative of secant x? That would be our little f over here. Secant x tangent x. So if you were ever asked, what's the antiderivative of secant x tangent x, you could say, oh, that's just secant x. But see, these are very special, right? These in green here. There's another one that we would know.
For Professor, for the antiderivatives, will we ever use the arc, like arc sine?
Yes. Yes, those will come into play. Yes, they will. This is cosecant x. So the antiderivative of negative cosecant x cotangent x is cosecant x because, again, we know that from Cal 1, the derivative of this is this. Now, I will admit that, well, I should not say admit. I will tell you, everyone in here should know that and that relationship because you should be very familiar with the tangent or the sine and cosine relationship with derivatives. And you should also know that the derivative of tangent was secant squared. These other ones may not be as common. Like you knew that they existed because I told you they did, but I'm not sure if you all memorized those by now. Most Cal 1 students haven't memorized these yet. The last one is negative cosecant x. And that is the derivative of cotangent x. Let's see. So I would say the ones here are probably ones that you should start to become familiar with, because if you see them, you're going to need to remember, oh yeah, you know, that's the antiderivative of, I'm sorry, that is the derivative of this. So you should be able to go backwards. So work on it, right? Questions? All right, so today we start something, we're going to continue, okay? We're going to continue with antiderivatives. We're going to start to turn the screws, all right? We're going to start to make this a little bit harder. And I stopped class last time with an example where I said, look, let's take some capital F, let's make it sine of x squared, let's take its derivative, and we got this. And then I said, well, let's act like we're starting here and asking how to go back to this. And I think that's when we ended class, and I really didn't have time to get into this. But the goal today is to show you the first sort of attack that you can implement whenever you're trying to do antiderivatives. All right. But before we get to that, I have to introduce some new notation. So it becomes kind of a pain in the ass to sit here over and over and over to be saying, find the antiderivative, find the antiderivative, find the antiderivative. Okay. So we have some notation that we use that tells you that I want you to give me the antiderivative of something. All right. And the notation that we use goes as follows. So new notation. So let's say we're going to start with a little f, okay, a little f of x, like that. And I want to tell you that I want you to give me the antiderivative of it, right? Here's what I'm going to do. I'm going to put this symbol out in front of it. All right, now that symbol, think of it as like an S, okay, the letter S that's been stretched out, okay? It's been stretched out. Now, if you take Cal 2, your Cal 2 professor will tell you, hopefully, that the reason they use this stretched out S is because later on we'll find out that this all comes from this idea of taking a sum. In the Greek letter, capital S, sigma, the Greek, capital S in Greek is sigma, this is it. And this actually turns out to be some weird kind of sum. And so that's why we use an S that's stretched out. But for now, for today, for right now, I just want you to understand that this is what lets you know that I want you to find the antiderivative of this, okay? Then there's one more thing I have to put in the symbol is times, all right, I'm gonna put here dx, all right. Now, right now, I don't want you to spend too much time wondering what dx is, other than thinking about it as it is the thing that tells you what the variable in the problem is. So our function was a function of x, right? And we want to take the antiderivative, treating x as our variable because it says dx, so that's telling me x is the variable. Okay? All right? We have names for these things. So let me bring up my notes, because I have my notes. I don't have to write all of this down again. Where is it? Here we go. Okay. So given a function little f of x, if we wish to find the general antiderivative, then we will write this symbol f of x dx. And so what that should be equal to is capital F of x, that's the antiderivative, plus some constant, right? This whole thing together, the whole symbol on the left-hand side of that equation is called the indefinite integral. Everything that's underlined is a new word for you, okay? This symbol is called the integral sign. The function you are trying to find the antiderivative is called the integrand. The dx is called technically the differential, and we'll explore that later. Capital F of x is the antiderivative of f of x, so that is the answer. And c is called, that c that we have to add for every antiderivative is called the constant of integration. So all these new words, isn't that fun? The process, the actual procedure that we are doing of finding antiderivatives of functions is called integration. So Cal 1 was all about differentiation. taking derivatives, differentiation. Cal 2 is all about integration, the reverse process. All right. Now, we've already explored the power rule. So this power rule right here, I'm going to copy it because I want you to understand this the way it's written, because that's the way it's presented most of the time in a book. The power rule says that if, and I'm going to write a specific example underneath this. Let's say we wanted to know the antiderivative of, let's say, x to the 7th dx. This is saying that the answer is going to be one of two things. First of all, if n is not equal to -1, so n is the power. Do y'all see n is the power here? Our power is 7, right? So we would be using this top, because 7 is not equal to -1. So we would be using this top one, which would say we need to do 1 over whatever the power was plus 1. So 7 plus 1, x to the 7 plus 1 plus c, which gives us 1/8 x to the 8th plus c. And that's kind of the formula that we came up with last class. I think Elise was the one who did that, who like said, you see a pattern and you add 1 and you have to multiply by 1 over that on the outside. That's basically the power rule. This rule works for any power of x. I'm sorry, yeah, any power of x, except there's one exception, okay? The one exception is when that happens to be -1. When it's -1, then that really is just 1 over x, isn't it? X and -1 is 1 over x. And that's the special one you have to remember. So if that power is -1, then our answer is just natural log of x. This has absolute value of x. Don't worry about it. If you just put natural log of x, I'll be happy right now. In Cal 2, they'll tell you, eventually they'll tell you need the absolute value around it. Okay, this right here, this rule is called the power rule for integration or for antiderivatives. And we should all now be somewhat comfortable with this. If we ever see something where it's x to a power, we're happy because we can find the antiderivative using this. Okay? The other things we should be comfortable with is page 6 of our formulas, or page 6 of the formulas. So let me go bring up page 6 of our formulas. So this, yeah, this is a good opportunity for us to look at our formula sheet. Here's page 6. We have what is called the table of integrals. And now of these formulas, let me show you the ones that now should make sense to you. Now, I should point out, notice in all of these formulas, they're using u instead of x. So instead of using x's, they're using u's. So look at, ignore number 1. Number 1, we're not ready for. Number 2, do y'all see this is really like x to the n? And do you see the answer?
Mhm.
That answer is really 1 over n plus 1, u to the n plus 1. What they did is they slid the u to the n plus 1 up on top of this fraction. But that's the same formula I just showed you. That only works when n is not equal to -1. So that formula should make sense to you now,
So why do they use u instead of x?
because of what's coming.
Or
We're going to be
substitution.
doing substitutions later. So we want the formulas to be more general, where that thing the thing that's being raised to the n could be anything. It doesn't have to just be x. Okay, so the next one is basically this right here. It's hard to see it. This right here is really 1 over u du. So they slid the du up on top. And that's just like the 1 over x dx we just talked about. And the antiderivative is natural log. Okay, so that one should make sense. Next
Is it
one,
okay with you, Professor, if we can write this on our formula sheets?
right, what?
This,
All this?
or, yeah,
You can,
Just to
well,
understand it
no,
better.
you can have the formula sheet. You can't go start writing a bunch of stuff on it though. I'm just trying to get you to see there's a connection here to what we've done. This one is saying, what's the antiderivative of e to the u itself, right? This one, haven't done yet. Antiderivative of sine of u, negative cosine u, yes. Antiderivative of cosine, sine, yes. Antiderivative of secant squared is tangent, yes. Antiderivative of cosecant squared is negative cotangent, yes. Yes. Yes, and then no, the rest of the way. Everything else is no. All right, stay tuned. These first ones, these first few we should be comfortable with, all right? 2, 3, 4, 6, 7, 8, 9, 10, and 11. By the way, I said we don't know what the antiderivative of tangent is, right? I said we don't know. Just FYI, here's what it turns out to be. It actually turns out to be natural log of secant u, but we can't show that yet. Okay, so where am I? There I am. Okay, so we should be somewhat comfortable with the formulas for on that page. Not all of them, but some of them. All right. So now we are going to finally get into this new idea of how do we do something more complicated. And when it comes to Cal 2 in trying to find antiderivatives, you have the power rule, which I've already given you. You've got the shit that you already know because of Cal 1. Okay, that's its own group of stuff. And then you have procedures, these attacks that you try. I don't know how to explain this in an easier way. Cal 1 is mechanical. I could teach a monkey how to do product rule. I could teach a monkey how to do quotient rule and chain rule because it's a procedure and it's the same thing every time. Product rule never changes. It's always the same, right? Product rule is product rule. Now, whether or not you recognize it's a product rule, that's something else. But the product rule is the product rule, right? You execute the rule, it's over. You execute the chain rule, it's over. Antiderivatives don't work that way. It's not a rule that I give you, and then you just go and execute the rule. It's almost like you just have to have some sort of intuition. It's very difficult to teach intuition, but in my experience, it comes from people who are very comfortable with the derivatives. That's what makes you comfortable going backwards. So in Cal 2, you will learn what's called substitution, okay? That's the first approach you can use. Then you have integration by parts. Then you have trig integrals, trigonometric substitution, partial fraction decomposition. Those are the 5 general approaches or techniques that we teach to teach students how to do integration, okay? Substitution, integration by parts, trig integrals, trig substitution, partial fraction decomposition, right? Today, I want to introduce you to the first one, which is substitution. All right. And each of those techniques relies on the previous one to be good at this next one. So if you can't get substitution, you won't be able to do integration by parts. If you can't do integration by parts, you won't be able to do trig integrals and trigonometric substitution. Does that make sense? So it's very easy to fall off the truck in Cal 2. You fall off early, there's no catching up, there's no making up. So I'm not trying to scare you all. I'm just I want you all to do well, but I want you to understand it's going to require a lot of effort. Okay, here we go. So how does substitution work? Where is it? I just took it off the page. Like I said, substitution is a strategy. It's not a monkey see, monkey do product rule, let's go, right? It's a strategy. And it's hard to teach strategies. So this is my way of teaching it, okay? I tell everyone, look, here's how you're gonna do it. You're gonna look at the integrand, right? Let me copy these steps and then we're actually gonna do a problem with these. If you like puzzles, if you like, solving problems that take some sort of clever little thing, you're going to love Cal 2. Okay, so here's what we're gonna do. I'm gonna give you a problem right now, okay? I want us to do the problem that we started last class, but we didn't get a chance to finish. All right, it was 2x sine of x squared, and then dx. So last class, I gave you what's in yellow. And I said, hey, let's try and find the antiderivative of that. This stuff in the front and the dx in the back, at this point, those just let you know, I want you to give me the antiderivative, right? You with me?
Yeah.
So what we're gonna do for this strategy, we're gonna first make sure it's not something simple, right? There's no power rule here because it's not just x to a power. This is not something I can just look at and be like, oh yeah, sure, that's just the derivative of this, right? So I kind of have to roll through the things I know. It's nothing I know, right? So now I go to my first strategy, which is use substitution. So for this substitution, I'm going to look at the integrand. Everyone looking at it?
Mhm.
Look at it. Look at it. Okay, we're looking. Try to find something. I'm not telling you what it is. Just try and find something, and also its derivative. Meaning the something that you see in there, I also want you to also see its derivative there. So does anybody see in this integrand something and its derivative?
Negative
Yeah.
Squared
cosine.
into x.
Sorry, I heard a couple of different things there. Go ahead again. Whoa.
Do you mean like the x squared and the 2x are related?
Yeah, the x squared and the 2x are related, aren't they?
Yes.
So the x squared is kind of like the something I'm talking about.
The u?
Well, hold on. I haven't talked about you yet. That's something, isn't it? I'm just following these steps. Try to find something and its derivative. Do you all see that this is the derivative of the something that I just found? Right? So I found something, x squared, and I noticed that its derivative, 2x, is also there. Okay, so you all see step 2, I've got it. Like I've got something in its derivative. I see it. I can see it with my eyes. Yes. If that's the case, I go to step 3. Okay, the derivative. The derivative is the part in green. This derivative part should appear in the numerator. So is 2x in the numerator of this expression? It's not even a fraction. Okay, so it's obviously in the numerator. Yes. And it's not trapped. Now, what do I mean by trapped? I mean, it's not like stuck underneath a square root. It's not inside of a trig function. It's all by itself. Okay, do you all see that the 2x is all by itself? In fact, if I wanted to, I could rewrite the problem like this. That 2x didn't have to be out front, right? I could have just slid it over to the back and it would have been the same thing. So it's not trapped, right? It's not trapped anywhere. It's in the numerator. I'm good to go. So I go to step 4. This is just a little note to ourselves. The derivative might be off by a constant. So remember, this something was x squared, right? The derivative of x squared is 2x, and I have 2x, don't I? If I would have a 4x out here, it would be okay. Step 4 is saying, hey, look, it's okay if the derivative is off by a constant, but it has to be only a constant, a number. So again, if this is x squared and I would have seen 4x out here, I would have said 4x is almost 2x. We're just off by a constant. Does that make sense? And we'd still proceed with the steps. All right, last step. Well, not last step, step 5. I'm going to let you, I'm going to make a substitution now. I'm going to let you be equal to the something that I said it was. Okay. So here we go. This is it. All that was just leading us up to the actual process. So I'm going to rewrite. Here's the problem. I'm going to put that 2x in the back. And here comes the substitution. Now, when I do substitution, I usually write next to it. I like to do the substitution next to the integral. So I'm doing this as like work on the side here. I'm doing a u, what I call a u sub or a u substitution. So here's the u substitution. I'm going to let u be equal to x squared. I've just chosen that I'm going to replace x squared in the problem with u. Now, next step, I'm going to do implicit differentiation on this equation with respect to x. Now you may be like, oh shit, implicit, what are we doing? I'm just going to take the derivative on the left side with respect to x and the derivative on the right side with respect to x. So the derivative of u with respect to x is du dx, and the derivative of x squared is 2x. Still with me?
Yes.
Next step, I'm going to get rid of the dx down here by multiplying both sides by dx. Got it? Now check this out. Do you all see that that x squared is really just u, right? X squared is just u. And do you also see that 2x dx is exactly 2x dx? Do you see that that's du? So what I can do is replace. I'm going to rewrite this integral completely. But instead of writing sine of x squared, I'm going to write sine of u, right? Because x squared is u. And then instead of 2x dx, I'm going to write du. But what is this asking us? It's saying find the antiderivative of sine of u, treating u like the variable. So what's the what's the antiderivative of sine? Of
Negative
u.
cosine,
Cosine.
Negative cosine of
u.
U.
right? Plus some constant. You know what? I just realized this is not the problem I ended class with last time. I apologize. It's a new problem. Who cares? Are y'all following me though?
Yes.
Okay, this should be the answer, but the problem now is that the original problem had x's in it and my answer has u's in it. So now it's time to substitute back. What was u? What was u?
X
X
squared.
It was
squared.
x squared. Okay. There you go. Plus c. That's our antiderivative. Now, is it correct?
Yes.
How do you know?
Because you can take a derivative.
Take its derivative.
Derivative.
So if I asked you now to take the derivative of this, of course, the derivative of a constant is gone. But what's the derivative of, let's ignore the negative. The derivative of cosine of something, right, would be negative sine of it. So if I took the derivative, I would have the negative from out here, but then the derivative of cosine of something is negative sine of it, chain rule, times now the derivative of what's inside, which is 2x. And what do you get at the end here? The negatives go away. You get sine of x squared times 2x, which was the original problem. Understand?
But I do have a question about the constant business. You said that it's okay if it's off by a constant. So you said that it's okay if
Let me do one. Let me do one.
Okay.
I think it's just
Okay.
easier if you see it. Yeah,
Okay.
it's much easier, I think, if you just see a problem. Okay, so how about this one? I want the antiderivative of x over the square root of 3x squared plus 1 dx. All right, let's first make sure that this isn't something simple. Can I like break this up and do like individual x to powers? No,
No.
right? Because I have a square root with plus inside. I cannot split that into two roots. And even if I could, I then couldn't split this into two fractions because I only have one term on top and two terms on the bottom or something. I still can't split it. And this isn't something that you should know from Cal 1, like sine or cosine. It's not something simple. So the only other thing you have right now is u substitution. How many things did I say you'll have in Cal 2? U sub, integration by parts, trig integrals, trig sub, partial fractions, 5. What makes Cal 2 very difficult, I mean, one of the things that makes the exam difficult is that by the time you get to the exam, you got 5 techniques. So you go and you see an integral and you're like, which do I use? You have to identify it. You have to have that problem recognition, and that becomes hard. But okay, baby steps, right? You got to crawl before you walk. All right, so we're going to look at this. We're like, looking. Does anyone see something in its derivative? It's okay to be off by a constant, but the derivative can't be in the denominator and derivative can't be trapped.
The something should be x squared and the x is the derivative.
Okay, so the something should be the x squared, and the derivative of x squared is what?
It's going to be, well, it would be 2x, but it can be off by a constant.
Okay, does everyone see that? X squared, let me highlight this. Don't highlight this on your own. If that was u, do y'all agree the derivative of that would be 2x, and I have an x up here? So I'm off by 2, but I have the x. So does that look like that's pretty good? Yes? Let's try a little more. What about if you incorporated the 3 also? What about 3x squared? What would the derivative of that be?
It would be 6x, but it would still be
6x.
fine.
And you'd still be fine because you're only off by 6. So the 3x squared would also work, wouldn't it? Let's go even crazier. How about the 3x squared plus 1? What's the derivative of that? Still 6x, right? Still 6x. And so what you want to do here is grab as much as you can without grabbing too much. All right. So could we incorporate the square root also? What would the derivative of the
setting it
square
to
root of all that?
Could we like change it to like to the 1/2? Would that make a difference?
Yeah, you could. I mean, no matter what you do, my question is more of, if you incorporate the square root as part of your u, when you take the derivative of that, don't write this down. If I incorporate the square root in there as my u, when I take the derivative of this, is it still just 6x? Am I just going to be off by a constant? No, the derivative of this would be rather complicated, isn't it? Because the derivative of square root is something, there's a bunch of stuff, chain rule we have to do. So I think if we incorporate the square root, it's too much. So what I'm going to do is I'm going to go with what I have in yellow there. I'm going to let that be my u. I'm going to make a u sub here. I'm going to let u be equal to 3x squared plus 1.
So it's okay to leave the square root out because it would make things more complicated.
That's right. It would be for u substitution to work, you need to see something in its derivative, right? So if you grab too much for u and you take its derivative and you don't see it there, then you can't use that for u.
Oh, okay.
So let's take the derivative here. So this is where I said du dx equals 6x, right? And then remember what I did next? I multiply both sides by dx. All right, time for us to play a game. This integral is the same as 1 over the square root of 3x squared plus 1 times x dx. What I'm doing is I'm sliding this x out here next to this dx just to make this a little easier to see. Can you all see that we have u here? That right there is what u is going to be. And be careful here. X dx is what I have in green, right? That's x dx. But we don't have the 6, do we? So watch what I'm going to do. Real simple. I'm just going to divide both sides of this little equation by 6. See, this is an equation. I divided by 6, or I multiply both sides by 1/6, and I got rid of the x on the right, or the 6 on the right hand side. So now I have a new expression here for x dx. So if you're ever off by a constant, see, we were off by 6. If you're ever off by a constant, you'll always be able to do something on both sides right there to make it match. So let's continue here. I'm ready to rewrite the integral. This now becomes 1 over what?
U, the square root of U,
Square root of u times, and what did x dx become?
1/6
1/6.
1/6 du. Anyone have any questions on that? Check this out. Okay, what did I do here?
algebra.
Yeah, algebra. I brought the square root of u, rewrote it as u to the half, and I brought it up like this. The 1/6 is just a number in front of it. So now I've gotten myself to a point where I can now use what to find the antiderivative of this?
Substitution.
The power
We
rule.
use substitution to get here, but what rule do we use now?
Can we use
I thought I heard it. Power rule, right? This is our power rule.
right?
We have a constant in front. We have, this is like x to an n power. We did this last time, right? So at this point, I'm ready for the antiderivative. It's time. So the 1/6 comes for the ride.
That's
And
not-
now the power is, the power we're working with here is -1/2. So that's like the n.
Positive.
So I have to add 1 to it, right?
Yeah.
So I'm going to put 1 over -1/2. I'm going to go slow here. Plus 1 u to the -1/2 plus 1, all of this plus c. This becomes 1/6. Okay, when you do -1/2 plus 1, that's a half. And 1 over a half is 2. U to the 1/2 plus c. The 2 over 6 becomes 1/3. And then isn't this really just the square root of u? That's square root of u, isn't it?
Yes.
So I'm going to put the square root of u. But what's u? I'm ready to go back to x. U was
3x
3x squared plus 1.
3x squared plus 1. There you go. That's it. That should be it. Let's check. Because that's the great thing about this. We can always check. But the only way you can ever check your answer is if you're good at the Cal 1 part, right? Because if you still can't take derivatives, then how are you ever going to check your answer? Okay, so I'm going to check it real quick. Take the derivative of this. 1/3 is a constant sitting in front. The derivative of the square root of something is 1 over 2 times the square root of that something. Times chain rule, derivative of what's inside is 6x. What happens here? See, 3 and 2, that's 6, right? On the bottom, that 6 cancels with that 6. And so what you're left with is an x on top, and then the square root of 3x squared plus 1. And that was the original integrand, wasn't it? That was what we were looking at in the very beginning. Okay. Ready for another one?
Yes, I need another one.
I have
Can
it.
you go back for that last one?
Yeah, yeah.
a moment? Okay, I got it. Thank you.
Okay. So on this one, let me do this. All right, I'm gonna throw you to the wolves here.
Thank you.
Nah, it won't make it too bad. How about we do? think I've already forgotten something. Hold on. All right, why don't I give you a moment to think? I hope that you're already seeing, just in what we're doing here today, that this is not robotic. This is not just do product rule F prime G plus G prime F, right? You actually have to think. Okay, I think that that's enough time, at least for now. Well, anybody see it?
Um,
X and the 1 over X.
Yes.
oh, I saw the.
What do you say,
LNX and
Austin?
1 over X.
Natural log of X and 1 over X.
So Austin is seeing that the something is the natural log of X, and that its derivative 1 over X is here also. I
Yeah.
agree. I think it would be best if maybe we rewrote this problem in a way that we could really express what Austin's seeing. Cosine squared of natural log of X times 1 over X dx. Because this is all multiplication on the bottom, right? This is really multiplied down there. We are free to use just algebra to rewrite this way. And so now does everyone see natural log of X and its derivative 1 over X right there? So let's do a U sub here. I like it. U is natural log of X. And then du dx would be the 1 over X. And that means du would be 1 over X dx because we multiplied dx on both sides. We can replace the natural log of X with u. And it looks like we have a direct, clean substitution. We're not off by a constant at all, right? And so this should go pretty good. Integral 1 over cosine squared of u du. So far, so good, or no? Any questions?
So I wrote my thingy as, so I had my u as ln x, and then I put u and the derivative little sign. Is it okay if I write it like that, or is that just gonna fuck everything up later on down the line?
What do you mean u, the derivative sign?
Like, you know, like u and then
U
the little
prime?
dash.
You
That's
put
the
u
word,
prime
my
here
bad.
instead,
No, when I wrote it out, I don't know how to explain it.
right here?
Let's see. So I put that, and then I put u to the whatever.
Yeah, don't do
Is
that
that-
because
okay.
we need Leibniz notation, this notation, so that we can reasonably understand where the dx comes from,
Okay, breaking it.
right? Because that dx actually comes from this notation. And if you just write u prime here, you're never going to have a dx. So you'll never have a dx over here.
Okay,
Okay, now what?
Taking the antiderivative.
we put everything in there.
You know the antiderivative of that?
Wouldn't we put in our u back in there, ln x, right?
Well, we haven't taken an
And
antiderivative.
oh, damn
Right.
it.
All we did was rewrote the integral. We have not actually found the antiderivative.
Is that on our formula sheet?
That's just secant squared.
Ah, okay, good. Elise notices this is just secant squared of u. Okay, so you have to now remember 1 over cosine is secant, right? So 1 over cosine squared is secant squared.
Derivative of that is tan.
And then you have to know this. This is where the little light bulb has to go off. Oh, I learned that in Cal 1. I know now that the antiderivative of this is tangent of u plus c. So look, when am I getting rid of the integral sign? When am I not writing it anymore?
Once
Once you've taken the
answer,
derivative,
When I'm taking the antiderivative. When I'm actually doing the antiderivative is when the integral sign goes away. Students always ask me, no matter how many times I've taught this class, almost every semester, students will say, look, I understand that when I go from here to here, the integral sign goes away. But students will always say, where does this go? Okay, this, don't worry about it, but if you need it to go somewhere, if in your mind you need it to go somewhere, then just say that that becomes the plus c, okay? And technically, that's not what's happening, but if you need to kind of somehow reasonably understand what's going on with this, it just becomes plus c. That'll help you not forget it. This is just the antiderivative, and that becomes the plus c. Don't tell anyone I ever told you that, though, okay? Because that's not technically right, but it'll give you the right answer, okay? All right, we good? Now, oh, we're not done. Our answer cannot have u in it. That's like me asking you what your favorite color is, and you say 3, right? It's a different variable, doesn't mean anything to us. So we got to take it back to x. Now, if you don't believe that that's correct, then just take derivative of it, and I guarantee you'll get it. It's fun, right?
yeah, it's not that bad right now, but I know you're gonna kill us later, so that's fine.
I'm not going to kill you.
Just hurt us really bad.
The course will kill you. It's not going to be my fault.
Okay.
I'm just the messenger. Okay, how about another one? Yeah, okay, let's do this one. 5x times cosine of x squared plus 1 over sine cubed of x squared plus 1 dx.
So I have an odd question.
Go ahead.
So since it's multiplication, can you take a cosine and a sine out to make it a cotangent?
You could algebraically. So what's being asked here is, since there is a cosine of something over, there's actually 3 sines here, aren't there? Could you take one of the sines out and put the cosine over the sine and make it a cotangent? Yes, you could. Now, is that going to be beneficial? I don't know, but algebraically, that's legal.
Would
So what-
I
We'll go for it.
go ahead? I'm sorry.
I was saying, once you do that, you would have 1 over sine, well, 1 over sine squared,
Mhm.
which you can change that to, I think secant squared? Or
Cosecant.
squared? Cosecant
Yeah.
squared, yeah.
It might, I mean, you might get somewhere with that. Now, I would not go down that road. Me personally, immediately, I would not go down that road. I'd be thinking, do I see something in its derivative?
Oh,
That's what I'd be thinking. So, you know, do you see anything in its derivative?
I have a quick question.
Yes, I'm sorry.
Could we look at this as like, hey, I see a chain rule in there. Do I undo it, or do I just look at and try and find something, like find the something at something instead?
Well, what we're trying to do is undo the chain rule, right?
Okay.
That's ultimately what we're trying to do. The problem with it is that it is very difficult to undo the chain rule by just looking at it.
I see
I-
what.
You couldn't
I
go
mean-
like outside in versus like inside out or something like that. Do the opposite.
It's too
of
hard.
whatever.
It's too
Okay.
hard to do. I can tell you right now, that's too hard to do. This is like negative, hold on. This is like, I can't even do it in my head. I think it's like -5. I think it's -5/4 sine to the -2 of x squared plus 1. I think that's the answer. But I can't look at that and get you the answer by trying to undo the chain rule. I mean, I could if you sat in here and let me
Okay.
look at it for a minute, but we definitely don't want to sit here and try and just look at it. We want to do something that's going to help us get there more efficiently, which is use substitution.
Okay.
The something would be the sine and the derivative would be the cosine.
So you see that
Oh.
that if you let u be sine of something, the derivative is cosine. I agree.
Because when you're doing the derivative sign, you could take the 3 out front, but that would just be a constant. You can get rid of that and the cosine up top.
Okay, so I'm gonna take a couple
What
of,
about
hold on, I'm gonna take, so here's one approach. Let's see if this works. You want u to be what?
Sine cubed and then the inside.
Sine cubed of
Oh.
x squared plus 1.
Yeah, yeah, no, yeah.
You want the whole thing, everything. That's the whole bottom. Remember about that? Let's see if this will work. If we take the derivative of this, we have to do chain rule. Right? The 3 comes out, sine what? Squared of x squared plus 1 times, now you can take
2x.
derivative of sine, cosine of x squared plus 1. Now you take derivative of the inside of that, 2x. Okay, did this work? So we let u be equal to this, right? Do you see this with what's remaining? So this is the something. Do you see its derivative? This is the derivative of it, right? Do you see all of that here? I don't. I see it here, but I
No.
see some other stuff here that's not here. Do y'all see that there's a sine squared of x squared plus 1 here that's not over here?
Could we use like terms? Or
Do
do
you
we have
see
to
that they're
find the
off?
derivative?
Oh, hold on. Do you see that we're off? Does everyone see that we're off? Does everyone see we're not off by a constant? We're off by a bunch of shit. We're off by all of this, right? Like all of that, I don't have that anywhere. Understand? So although I like the idea of maybe using sine, I think we grabbed too much by grabbing the cube because that with the chain rule left us with the sine squared in there. So maybe we back up. Maybe we try again. Danielle, did you?
Can I separate it? Like 5x? Would it make a difference if I kept the 5x there and then I moved the 1 over sine cubed into like 1 over that? Would it do anything for me? Or
It
would
might
that
help
just-
you, it might help you visually to see things. I mean, maybe you want to do this. Maybe you want to write 1 over sine cubed x squared plus 1. Maybe you want to write the cosine of x squared plus 1, and then maybe you want to write the 5x dx. Yeah, if
Yes,
this helps you kind of see everything, that's fine. There's nothing wrong with that. You don't
Okay,
have to do it. It doesn't mess anything up as long as you don't rewrite it incorrectly. So let's try something else. Sine cubed was too much, right? So what maybe can we try instead?
Can you separate the
Can we-
signs into 3 different signs?
You could.
and then have it?
Do that and then just have a singular sign be something for the cosine.
Okay, everyone just take a deep breath. I think y'all are trying too hard to find the u substitution. I'm asking you to find me anything and see its derivative somewhere. And y'all are trying for way too much.
X squared plus
X
1.
squared plus
Square
1.
plus 1,
Squared plus 1 and 5x.
and the derivative of that is 2x, we have 5x. Does everyone see that?
Yeah.
Okay, let's start with that. I think that's The easiest substitution is C off the front. If u is x squared plus 1, right? The derivative of that would be what? 2x. All right, bring the dx to the other side. All right, I'm going to erase this yellow. So here's where we are. I'm gonna write it the way Danielle suggested we write. I'm gonna peel everything apart. I want to highlight in yellow everything that's going to become a u. This becomes u, and that becomes u, right? Both of those get replaced with that. Okay, so everything yellow is going to become a u. Now, here we have 2x dx, but here we have 5x dx, don't we? So is there any
Yeah.
way that you can make this in front here a 5 instead of a 2?
You can pull something out, right?
You can do whatever you want to both sides of this equation. How about I hit it with 5 halves on both sides?
Yes. Okay. Yeah.
If I do that, what happens? 2's cancel, right? The left side is 5 halves du, and the right side is now 5x dx. Isn't that clever? Right? Just
Yeah.
scaling it so that it makes it match. See, I'm playing a little matching game. This is fun.
Quick question.
Yep.
So it's okay because as soon as I saw the problem, I saw x squared plus 1, x squared plus 1. They're not derivatives of each other, but they match. That's okay. Like as soon as I see that, that's fine for me to use that as my u, even though that's not a derivative of
The
any of
only
this.
thing you need to see is something and its derivative, and you can be off by a constant. That's all you need to see. So x squared plus 1, you see it. Its derivative is 2x, you have 5x. You're off by a constant, you proceed.
Okay. So yep. Okay. Yep.
I have another question.
Yes.
So I know that if we grab too much, it can just not work out at all. But
Mhm.
if we grab too little, does that just mean that we're gonna have to put in more work, or would it
Yes.
also just not work out?
It means if you don't grab enough, it just means you're going to need to do more work, but it doesn't mean that you won't get to the answer. So eventually what you want to do is get to a point where you can see the most efficient substitution. The most efficient substitution in this problem would have been sine of x squared plus 1. That would have been the best substitution to start the problem with. But x squared plus 1 will work because it is something in its derivative. Let's continue. All right, so let's rewrite. Can we rewrite this integral? Integral 1 over. This now becomes sine cubed of u times cosine of u, and that becomes 5 halves du. Does everyone see where everything came from? Any questions on where anything came from?
No.
Okay, this next step I'm going to do, I have not done before, but I hope that when I do it, you'll kind of agree with me that it doesn't really change anything. Because when it comes to taking antiderivatives, just like derivatives, constants like 5 halves can come out and just be multiplied at the end. So they just can come for the ride. So I'm taking that 5 halves, I'm putting it in front of the integral sign with the multiplication. Does that seem reasonable to you that I can do that? Yeah?
Yeah. Just bring it all the way through till the end. Like,
Yeah,
like
and
how
we'll
you
just bring
say
it all the
like,
way to the end and just multiply it through
Yeah.
at the end.
just taking it for a ride the whole time.
Yep. Okay, so here we are. We look at this now and we say, all right, do you know the antiderivative of that? And when you look at it, you should look at it and go, no, I don't know the antiderivative of that. That's not something simple. But there's nothing that says we can't start the whole process over and try another substitution. So do you see something and its derivative?
Yeah.
Sine and cosine.
Sine and cosine?
Yeah, sine u and
Mhm.
cosine u.
Okay, so the derivative of sine of u would be cosine u, right? And the derivative of cosine of u would be negative sine of u, right? There's two different ways that I could approach it. So please pay attention. There's two different things that you could try here. Now, there's a problem. We've already used u, haven't we? So I have to use a different variable. I can't use u again. So I'm going to make a v substitution. One option would be to let v be sine of u. Another option that someone else might want to do is cosine of u. Which of these is correct, or can I use either one? So think about it. If v is sine of u, that's v's sine of u is going to be that, right? The derivative of this would be what?
Cosine.
Cosine.
U.
And do you see cosine?
Yeah.
Yeah. Is it in the numerator?
Yes. Yeah.
Is it trapped?
No.
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 That's good. How about this one? If we let v be cosine u, that would be this one up here, right? And the derivative of this would be negative sine. Do we see a sign? Yes,
Yeah.
right?
Yeah.
But where is it?
And
In the
denominator.
denominator. And it's trapped because it's being cubed. We do not want to do that then. Okay, so I do not want this. So I'm going to leave my substitution here and watch what I'm going to do. I'm going to go dv d what? Taking derivative of this
du.
with respect to u is cosine of u. Then I move my du to the other side. And I get a perfect match again. Oh, match made in heaven. Look at that. Perfect. So now here's where I am. 5/2 antiderivative of 1 over what?
V.
V what?
V.
B cubed.
V cubed.
V cubed. Okay.
Right?
Oh,
Because
shit, where did I go?
sine of u is v. The cubed was not part of the substitution. It was just the sine part. And then the rest of this in green is just dv. This becomes 5/2 antiderivative. Now I'm very happy to see a variable to a power like that because I can bring it up as a negative power. And then I can use my power rule.
The dv wouldn't be used as a power, right? Because it's not to the 1. We're just doing it on the v. Right?
Yeah, you're not doing anything to this. All you're focusing your
Okay.
attention on is this.
Okay, making sure.
So this will be times 1 over what?
-3 plus 1.
-3 plus 1, which is -2, v to the -2. So I hope that everyone's comfortable going from here to here. This is last class, right? Power rule. Plus c. Okay, we're getting there. We're almost to the answer. All right, so I'm going to just rewrite this. I have a 5 on top. On the bottom, the -2 and 2 multiplied together give me -4. And I'm going to move that v to the bottom. So it's v squared on the bottom plus c. Right now, my answer is in terms of v. The original problem was in terms of x. So I first needed to substitute back. What was v? V was sine of u.
Sine u.
So this becomes sine of u squared on the bottom. That's just replacing v with sine of u. And then what was u? We did that
Is that
substitution.
Squared plus 1.
X squared plus 1 plus c. I have to go back and watch my video, but I think I said that's what it was going to be. I think I said it's going to be -5/4 sine. I think that's
Yeah,
what
I think you
said.
did. Yeah,
So-
I think you
See, the thing is, I mean, but I've been doing this forever, and it's very difficult even for me to do that in my head and get all my constants right, because there's a lot of things that have to be accounted for, like this scaling, right, to make this become a 5x, and then with sine and cosine, there's negatives that pop out and stuff. So Woo, okay, that was fun. Now,
No, like
Elise had said something earlier about grabbing too much or not enough. If I challenge you to go work this problem again. Okay, but this time make the substitution u is equal to sine of x squared plus 1. Let that be your substitution. This will work in one step because the derivative of this would be chain rule, right? So derivative of this is cosine of this times the derivative of what's inside of it, which is 2x, and that's basically what you have up here. So can you kind of see what I was saying about how you can only really be good at Cal 2 if you can do the Cal 1? Because even in here, like, you have to take a derivative to even do this, right? If you can't take this derivative, you're in trouble.
no, I love it. I'm living for it.
All right, here we go. I have another one. Just when you think everything's great. Well, you know what? Yeah, we'll do it.
Do it.
Do
Do it.
This is the last topic we're learning, right?
Yes.
All right.
I want to start with this. So look, before you get carried away, do you all agree that I could square the x plus 1? Like I could actually do x plus 1 here squared, which means I would take x plus 1, multiply it times itself, and just do some algebra and make that x squared plus 2x plus 1. Right? I could do that with this. And then I could multiply an x through that, couldn't I?
Yes.
This x out here could just multiply through this. So I could, if I wanted to, convert this problem into x cubed plus 2x, I'm sorry, x cubed plus 2x squared plus x dx, and then just figure this out. Do you all agree I could do that? Understand what I did? Just take that, boil it out, get that, distribute the x through, and then each of these, check, check, check. I could do them individually because there's plus signs between them. Power rule, power rule, power rule, right? No issues?
Yes.
Gotcha.
Okay. So no substitution there. That was just good old fashioned algebra with a little power rule. What if I change the problem? To that. Now, do you feel like doing that algebra? Do you feel like doing x plus 1 times x plus 1 times x plus 1 200 times? And then after you do that, distributing an x through?
I mean, it was,
No.
Okay, so take a minute to look at this, okay? Because no algebra that you have, or you don't have enough time, okay, to do that algebra, is going to save you here. And the only other thing you know is substitution. So I want you to just take a moment to see what you think, and maybe we can figure out something to do and just see what's inherently problematic with this. We'll take a minute and a half. All right, does anybody want to share what issues they're having with this in terms of trying to follow this procedure.
Oh, well. Oh, wait, is the one trapped?
Yeah, that one's in there with the X.
To the 200, so it's trapped, right? Is that what you're saying, Cody?
Yeah.
Like, so we can't just take it, like, out.
Yeah, you can't.
Because
take
X
that.
plus 1.
'Cause I wanted to
Yeah, 'cause-
say that the X could be something and the 1 could be the derivative, but then I just realized it was trapped.
Okay, I see
yeah,
what you're
'cause
saying. Like
X plus 1 is the
if
derivative.
U is X, then the derivative of that is 1, and you see a 1 here, but yeah, then it would be trapped.
But well, then couldn't we just separate like one of the x plus ones from the other 200 and then do it like that?
Separate one of the X plus ones from the other, and then do what?
And then one would be the derivative of x because it wouldn't be trapped anymore from the 200. Well, it'd be
It would
190.
still be in the, it'd still be with an X plus 1. It wouldn't be a 1 by itself. When I say not trapped, I mean it would have to be able to be slid out here to the back. Like the 1 would have to be back here. Which there actually is a 1 there, isn't there? There's always a 1 there.
Yeah. Can I take this dx? Does that mean I could take the derivative of like x or something like that?
Yeah, could X be the something and the 1 before the DX be the derivative?
Yes, it could.
You know what I mean?
Yeah, but okay, so don't write this down. I'm gonna do it and then we're gonna learn a lesson from it, okay? So
Okay.
could we do U substitution, could we let U be X? Absolutely, okay? Let's see what'll happen. Du over dx equals 1. That means du equals 1 dx. Right? Go with me?
Let's create a loop.
It's not on. Okay, so now everywhere we see an X, we can replace it with U, right? And everywhere we see 1 dx, we can replace it with du. Let's do it. This becomes U plus 1 to the 200th du. So what have you done?
Substitution.
Nothing.
Done nothing. Because
Yeah,
all
literally
you've done
done
is
nothing.
rewritten the problem now in terms of U. You've replaced X with U and you still have the same problem.
If you squint hard enough, can you use the power rule?
You mean the regular
okay,
power rule?
you can't use the power rule, not directly, because of
No,
this U out here.
Hmm.
So hold on, let
Good.
me finish my lesson. My lesson was that
Okay.
when you're doing U substitution, never make the substitution U is equal to X, because you'll wind up with the same exact problem. All right. Now, what should be the troubling part of this is I've been telling you, look for something in its derivative, look for something in its derivative, and it doesn't seem obvious what we should choose for U, right?
U plus 1? Or X
Maybe
plus
U
1?
plus, or not U plus 1, maybe X plus 1?
Yeah.
Does that change anything? I don't know. Let's see.
The 200. Well, that is like how the u on the outside has a 1, right? As its exponent, and then the other one has a 200. Can we do something about that? Or am I just
This
like,
and
thinking
this?
about things? The 200 and then the u that's on the outside, like 1.
Yeah.
Like that there's 1 and then there's the 200, and I don't know where I'm going.
You
with
can't
this, but I
combine
just
those
used that.
together at all because this right here is plus 1 and so you have to expand that out first. There's no way around that algebra. You have to do all of this first. Order of operations. You have to do exponents first. So you have to do all of this to the 200th power before you can do anything else.
Okay.
So let me go back to the original problem and let's make this substitution U is X plus 1, which doesn't seem that much better than just doing X, right? It doesn't seem like this can be much better, but it's going to work. Okay, watch. Du over dx is equal to 1. That means du is equal to 1 dx. Let's do the same substitution. Be real careful here, everyone. Watch. X plus 1, that's going to be u, right? This 1 that's next to the dx, that's going to become du. That okay? The only thing we have not accounted for in this problem right now is x. We can't leave x in here. Look, if we're going to make a substitution, everything has to switch to u's. You can't have u's and x's mixed together, okay? So I have to replace that x with something that has u in it. Do y'all see what I'm going to do?
U plus
U
1.
minus 1.
Yeah, I'm going to take this equation right here. I'm going to solve it for x. So I'm going to subtract 1 on both sides. Now I have an expression for x. I'll make this blue. X can be replaced with u minus 1. Watch, this is gonna be awesome. Okay, x now becomes u minus 1. I need that in parentheses. Then I have x plus 1. What is x plus 1 being replaced with?
U.
U to the 200th power. Don't forget the 200th power that's acting on the u. And then the 1 dx gets replaced with what? Du. And so you look at that and you're going to sit there and tell me, wait a minute, well, we didn't gain anything here. Or did we?
The 200 isn't trapped. The U to the 200 isn't trapped anymore.
That's right. Now I can distribute this through the parentheses. You see? I can distribute that. See, I couldn't do that up here. You might want to push the x in here, but you can't push the x in here because the 200 has to happen first. But because of this very simple substitution, which didn't seem like it was going to help, actually made this where now this problem becomes integral u to the 201 minus u to the 200th power du. So I just distribute. When I do u times u to the 200th, I just add 1 to the power. And then 1 times u to the 200th is u to the 200th. Now I've got two terms separated by subtraction, powers on both of them, power rule. So the antiderivative, no more integral sign, is going to be 1 over
We can't.
202 u to the 202 minus 1 over 201 u to the 201 plus c. Final step, what was u?
X plus 1.
X plus 1. There it is.
We couldn't actually like subtract anything from the u's because they're both u's and then the exponents are 201 and 200. We couldn't do anything with that.
You mean over
They're
here?
above the same. Yeah, because they're the same base or whatever.
Yeah,
We can't.
you
do
can
anything.
only do something if they're the same base if you're multiplying or dividing. Then you can
Okay.
add the exponents or you can subtract the exponents.
Okay, thank you.
Okay, so the moral of the story for this problem is that as soon as you start to think that you kind of get an idea of how U substitution works, where you're looking for something in its derivative, you see a problem where it's not obvious that you should make any substitution, but it turns out to work if you just make one. So I always tell my Cal students, my Cal 2 students, you have to be ready to fail in this class, like not fail the class, but you have to be ready to try something, and for it not to work, cross it out and try something else. And that doesn't work. And then you cross it out and you try something else. You're going to strike out more than you're gonna hit, okay? I mean, it's just gonna happen. It's just gonna happen in Cal 2. But as you do more and you start to practice, you start to get a comfort level where you start to see it, okay? It's very hard to teach this because it's hard to teach that intuition. So yeah, that's a fun problem. Let's look at the review for the final.
I actually like this better than regular
Old
derivative.
derivative
Yeah,
stuff.
it's not, this is a lot more.
I'll pick the
I don't know, I
OG
just like-
stuff.
Careful what you wish for.
Yeah, I know. gonna die.
Okay, so here we go. These problems are basic U substitution problems. Okay, both these problems, you should be able to look at them, see something in its derivative, and crank it
Yeah.
out. Now, I actually have the solutions to the review, even though I said I wasn't necessarily going to share those with you right away. I'm going to send those out tomorrow evening. I'm going to wait a little bit to let you all kind of go through, but I have all the answers to all the review. Okay. I'm not done with class. I'm just letting you know. We can now officially, at this point officially, we can do every problem on the review. Like technically, all right? There's nothing on the review we haven't talked about. Okay, so now I could do substitution problems all day. And this is out of section 5, chapter 5, section 5. I tell my students to do all 36 problems in that section, every single one of them, because there's no such thing as doing too many homework problems when it comes to integration. There's just no such thing. So, oh, yeah, no.
Are we gonna run into any problems that is gonna require us to try and think about arc sine business or no?
Yeah, yeah, but I don't want to address that in here right now. You have enough going on that you'll just pick it up in Cal 2.
Okay, so just ignore those.
Yeah, anything that has inverse trig functions in it, you can just ignore. Let me see here. I'm just saying if there's anything else here that I would want to do before I move on. This one's interesting. I think this one's interesting enough for us to look at. So I want to show you this one because it's a weird one, and it's the first time you're going to probably see something happen that you would have never thought to do. Maybe you would have thought to do it, but most people don't. And a lot of times in the Cal 2, there's going to be these times where you see, like, you're shown something and you're like, wow, I would have never thought about that. And then now it's like, now that you've seen it, you better think about it now because it's now part of the game. Okay. So what are you thinking in terms of a U substitution here? You see something in its derivative. What's that?
X squared plus 1.
X squared plus 1. Now its derivative is what?
2x.
2x. Now, do you see a 2x? Because I see an x cubed.
Maybe you could pull
Well, x is part of x cubed.
X is part of x cubed, right? So maybe we could pull an x out of the x cubed. Now, I think that might be a way we go. Let me ask you this. Why didn't you say x cubed though? Because if you say u is x cubed, the derivative of x cubed is 3x squared, and I see an x squared.
I mean, if we go that way, could we, it's trapped at the moment, but could we just rewrite the equation as like x squared or x cubed and then times x squared to the -1, x squared plus 1 to the -1/2?
Okay, good. Yes, but it would still be in that parentheses to -1/2, right? It would still be trapped in some sense. To be untrapped means that you have to be able to pull it out completely by itself, not attached or put into any other functions. Does that make sense, Austin?
Yeah, it does.
So I think on a problem like this, the tricky thing is you might want to say x cubed because the derivative of that's 3x squared and you see x squared here. But because the x squared is down in the denominator, it's trapped under a root, you do not want to go that way. The real thing to see is that if you let u be the x squared plus 1, the derivative that's 2x, which we don't see 2x unless we take the x cubed up top and peel one of the x's off to the side. So we just take one of the x's from here and just drop it here. And now I see it. Now I see the derivative of x squared plus 1. I'm off by a
Okay.
constant, right? I'm off by a constant. So u is going to be the x squared plus 1. Du dx is 2x, which means du is 2x dx.
Then we gotta multiply by a half, right?
Yep, and now I'm trying to match up. So I've got x dx here. I've got that right here. So I don't have a 2. So I'm just going to hit this with a half on both sides. That should get me the x dx on the right. And that half du will come in right there. So there's my green. So I can replace the green part with half of du, the yellow part with u. Uh-oh, what about the blue part?
Are we gonna have to use another variable?
Yeah, another variable.
Like again,
Minus
like a
one.
d of v?
No, we have to use a u. We have to, it has to be somehow in terms of u.
We can.
Just switch around the equation of u equals x squared plus 1.
Good, look at the very beginning, the substitution we made in the beginning. U is x squared plus 1, right? So we could solve this for x squared and we could get u minus 1 equals x squared. We're using the original substitution, the fact that x squared appears here, to figure out an equation for x squared in terms of u. So that blue part, x squared, will replace with this. The original integral now becomes the blue piece, u minus 1, over the square root of the yellow piece, which was u. And then the green piece is 1/2 du. And so you might be freaking out a little bit here. Don't freak out, because you have 2 terms on top and 1 term on the bottom. And I brought the 1/2 out completely. All right. And now you can just simplify these using algebra, right? This becomes 1/2 integral. This is u to the positive 1/2 minus u to the negative 1/2. Does anyone have any questions on how I got from here to here? Do y'all understand the algebra going on here?
Yes.
Power rule now. So no more integral sign. Here comes the antiderivative. 1/2 is going to come for the ride. So I'm just going to put everything, all my answer in parentheses. The antiderivative of this should be 2/3 u to the 3/2. I'm going to leave you to figure that out on your own. Minus 2u to the 1/2 plus c. So from here to here, that's the step where I actually took the antiderivative, right? Power rule on that, power rule on that. I'm going to now distribute my negative, or my 1/2 through. When I do that, I get 1/3 u to the 3/2 minus the 1/2 and 2 cancel, so u to the 1/2 plus c. And u in this problem, I believe, was x squared plus 1. Yeah, x squared plus 1. So there it is, x squared plus 1, x squared plus 1.
Are we gonna ever have to like fully solve that or something like that at some point?
No, we're not gonna have to like set that equal to 0 or anything like that. We will have to, you will have to like plug numbers into it, but you won't have to like set it equal to 0.
Okay.
Okay, so we have 5 minutes, 6 minutes. We're done with substitution. I could, like I said, keep going for like all day long, and it would just be fun, followed by more fun, but followed by more fun, but we're gonna stop somewhere, okay? All right, so now we have, I just want to show you something kind of like where this will be used, right? I told you that the area, somehow the area under a curve has to do with the antiderivative. So here's an example. Let's say we take the function f of x equals x squared. All right, and let's graph that function, that parabola. Let's graph it just on the interval 0 to 2. So if I graph that, it would start here at 0. It would go out to, you would go up to 4. If I want to find the area underneath this curve, this is just, since we're in the last 5 minutes, I'm just showing this to you just to give you the value of what we're doing here. To find that area, here's what I do. I find the antiderivative of this, okay? So what's the antiderivative of this? The antiderivative of that would be 1/3 x cubed, right? That's what it is. Now, plus c, right? Plus c, plus any constant. I'm going to use the constant 0. So that is one specific example of an antiderivative. To find this area, what I do is I take capital F, the antiderivative, and I plug in b, and then I take capital F and I plug in a. Now, what do I mean by a and b? Those are the
coordinates.
The endpoints of the interval. So I just have to plug this point 2 into the antiderivative and subtract from it what the a plugged into the antiderivative. So that means I'm going to take 1/3 x, which is going to be 2 cubed, and I'm going to subtract from it 1/3 and then 0 cubed. And this right here, this goes away because that's a 0 in there. This is 2 cubed, that's 8 times 1/3, it's 8/3. So I can tell you that the exact area underneath this curve, the exact area is 8/3. And this thing is later known as the evaluation theorem. And it allows you to find the area under any curve. So long as you can find the antiderivative, you can find the area under the curve. Are there any questions?
On our last problem with the square root on the bottom, would there be opportunity to use the conjugate maybe to help too, or no? That wouldn't help.
Normally with integrals, we don't ever introduce a conjugate to make it better. Not to say that it would never happen, but that's something that conjugate here wouldn't do much to help us. Probably make it worse.
Let's not do that then.
Yeah. All right, everyone. We're at that point where, I mean, there's not much more I can do at this juncture. So, yeah, your finals right a week from today. So you got plenty of time, and I'll be around. I sent out a thing, an email with my office hours that have been adjusted for finals next week. And yeah, I appreciate all of your attention, and especially those of you who kept your cameras on. I've made note of that, and I've also made note of people who, even though you didn't have your camera on, were constantly responding. I've always tried to keep a little note of that during class, and that will help you out with your grade, because it makes a huge difference just to be able to look up and see people's faces. So even though it's not a big deal to have your camera on, not everyone does, and I appreciate it. Hopefully we'll get back to some normalcy, you know, at some point. I think this will always be here. Like Zoom will always be a part of education now because it works for a lot of people, but you know, I'd rather be in the classroom where I can throw shit at you for not paying attention. You know, it is what it is. I appreciate your time and effort in doing this class this way, and look forward to the final. And down the road, if I see you in Cal 2, I see you in Cal 2. You know, if you take another instructor, it's fine. Whatever you do, my door is always open to you, even if you transfer out to another college. If you ever want to call and talk to me, send me an email about math or have some questions about anything, I'm always available to you. It always makes me happy when I hear from a student like 5 years later and they've now become an engineer or something. It's always makes me feel good. Like I'm actually doing this for a reason other than the fact I like it. But okay. So Study hard. Good luck on your other finals too.
Thanks.
Thanks. So we can meet up at 10, like your office hours on Tuesdays that starts at 10 a.m.
Yeah, I'm actually going to be there
Nice.
tonight too. I'm going to be here tonight, right? I think I said from 8
8
to
and 9.
8 to 9. I'm going to be here, and then tomorrow, twice tomorrow. Then in the weekend, if you need me, it'll be by request. And then Tuesday, what did I say for Tuesday?
I think it's 10 a.m. to 1 p.m. And I was just trying to see, like, while we're all here, like, are we all gonna join in at 10 a.m. together to
Whoever
go
wants
over
to be
things
there,
or
be there.
whatever? Alrighty.
Yeah, I'm going to send out the solutions. I think once I send the solutions out, some people are going to be like feel a little bit better that they're doing things correctly. But try and do as much of it as you can by yourself first.
I had a question, sir.
Yes.
Going back to the graph, like the explaining what the antiderivative like means, the area. What does that represent? Like, say that it was like a time distance graph. What would that, the 830?
Okay, so yeah, it would just depend on what it is. There's a lot of different ways to look at it. So, one good common example that kind of helps is if you have like force over distance, like if this is like, yeah, let's say you're applying some sort of force over some distance. So if you have a graph, right, like this, let me see if I can't relate this to, let me relate it to this first. Remember when this was distance and this was time? I'm sorry, other way around. When this was time and this was distance, when we went this way with the derivative, it became distance over time, which was velocity, basically, speed. So when we go backwards, right, when we go backwards, if this was velocity and time, and I think we were, who was talking about this last time? Oh, I think it was Elise asked, what goes, if you go backwards from distance time, what does it become? But the point I'm trying to make is when you go backwards, you're basically multiplying these two together. Okay, so when you integrate, you go backwards. So it'd be velocity times time, which gives you distance. So if we were to go, if this was force and this was distance, then to go integrate, right, to go backwards, to find the antiderivative, you multiply those together, and force times distance in a physics class is work. The force you apply over a directed distance is work. So the area under this curve would be the work done, the total work done to move an object with a certain amount of force over a certain distance. Does that make sense? So, but that can be anything. I mean, the area underneath a curve can represent so many different things. It all depends on what these two axes are, right? Another way would be, yeah, I mean, this one's not as fun, but I mean, if this is time and this is your speed. So let's say you're driving down the road and at every point in time, somebody's marking down your speed. Okay, so you have a graph that shows your speed at every point in time, right? So I know how fast I was going at every point in time. Well, if I find the area underneath this, that's how far I went. That's my distance traveled. Does that make sense? Yeah. So there's many applications to it. It's just depends on what you want to have on your X and Y axes, what those units are.
Yeah, so the area under the graph is just the two axes, like whatever they would multiply to be. So
multiply together to be.
Yeah, so velocity and time is distance. Okay.
Yeah. All right. Anything else?
I had a question on the example where you put in like u is to the 200th power.
Yes.
I was wondering, can you go over how you got let's see. Actually, you scroll down a bit more. Yeah, how did you get like 1 over 202 to u over 202? Like,
oh, power rule. So I'm doing the power rule on this. Okay, so like it's like when we had x to the 4th, the antiderivative of that, right? The antiderivative of this is you look at the power, you add 1 to it, right? So that's 5. So you put 1/5 x to the 5th.
Okay.
right? So I'm doing the same thing, but it's u instead of x, and the power is 201 instead of 4. So I
Okay.
just added 1 to it, 202, and then 1 over 202 out here. That makes sense?
Yeah, I didn't realize that that's when you started taking the antiderivative. Okay, I
Yeah.
got it. Thank you.
Yeah, so the reason you know that is because here the integral sign's here, and then when I get to the next step, it's not here. So that's when I actually did the antiderivative.
Also, so that just to remind you, like you haven't taken the antiderivative yet, the integral sign.
Sorry, say it again.
The integral sign is just there to remind you that you haven't taken the antiderivative yet.
That's right. Mhm. Everything we did up to that point was just to make it look like something we could take the antiderivative of. Like up to this point, we just like couldn't do it. And then we did some substitution. We're trying to massage it into something we can handle. And then we finally get it here. And we're like, oh, okay, finally, now I can do it.
Okay, so we're just like rearranging the problem until it's suitable.
Yeah, we're making a substitution that makes it look visually different and into something that we can handle so that we can find the antiderivative. And then once we get it, we switch it back in terms of x.
Oh, okay, I get it. Thank you.
Yeah.
Hey,
All right.
just want to make sure one more time. You said anything that has like anything trapped, let's say on this last problem,